We are going to fit a model for the data, but before we proceed with an example, a few things to know. I'm going to go with ax plus b because that's what the calculator has. But does it matter whether you call it mx plus b, ax plus b? No. What is a? B. So the objective of statistics, as I mentioned last time, is to find the value of a and b using the data that we observed for x and y. Of course, when we find those values, are they going to be the actual true values that explain the relationship between x and y? No, they are estimators. So how do we denote the estimators? Typically, anytime something is an estimate, what do? We put a hat. And both of those values are obtained using data. So once we have the values for a hat and b hat, I can put it in my equation. But whatever number that I would get by plugging in x is not the actual value of y. We call that the fitted value. Why do we call it the fitted value? Because we use the line of best fit, right? We use the data to find a hat and b hat. That's going to give me the line of best fit. So whatever value of y hat and y I get, it's rather an estimated value, estimated using the line of best fit. Last time, we obtained values of y, and then we did y hat. And they weren't the same, they will not be the same. So each observation in the sample is x1, x2, x3, x4, likewise y1, y2, y3, y4, and so on. So if I pick the ith pad observation and plug it in my fitted model, I will get the ith fitted value. And as I mentioned, the fitted value is not going to be equal to the actual y value that we used. It will be close, but it's not going to be exactly the same. That brings us to something called a residual, but doesn't have it. So I'm going to go with the actual explanation, literally. Actual value minus the fitted value. Remember in the picture that I drew, we had a bunch of lines and I wrote the sum of squares of the distances between the line of best fit and the observation is what we need to reduce, which is why we call it the least squares. So the residual simply is the distance between a fitted value and the actual value. Let's say I have observation number 10, hypothetically. If the residual is large for the observation number 10, what does it tell us about the model in predicting observation number 10? Example, maybe you could see that. Let's say the actual value, y10, is 72. I used the data, I got an equation, I put in an x value. Whatever my line of best fit gives is, say, 94.6. Yes? It is pretty far from the actual value, correct? So my question to you is, if the residual is large, what does it say about our line of best fit? It's not doing a good job in predicting y10. Does that make sense? So generally speaking, a line of best fit is not going to predict every single observation, with very small values of residual. There will be at least one observation that sort of doesn't fit the pattern. So what we would ideally want is a zero residual, but we're not going to get a zero residual. There will always be a residual. But overall though, if I sum all the residuals, it will always be equal to 0. Good. The reason being, when we have a line of best fit, some of the observations will be above the line, some below. And when I add the distances, it will simply become 0. Standard formula, the estimate for the slope is simply the value of r. We know how to find that. Multiplied by the standard deviation of y divided by the standard deviation of x. The estimate for b is the mean of y minus the value that you estimated for a multiplied by mean of x. Is it hard to find any of these? No. Sure, I could do all of that and estimate the value of a hat and b hat, but we are going to use the calculator to get those two values. Good.